Hello, and in this video I will be explaining the development and tuning for a Cascade PID controller for a Ryse Tello drone. A PID controller calculates a desired control output from an error input. The proportional part reacts to the size of the error, the integral part looks at the past errors, and the derivative part predicts the future error. In order to apply PID to our scenario, the equations must be discretized. A typical Cascade controller uses nested feedback loops to improve performance. The outer loop sets the target for the inner loop. However, a Cascade controller with a chain structure was used, as we could only control velocity and yaw rate. While Cascade PID reduces lag and improves responsiveness, it adds complexity and is harder to tune. This plot shows the drone reaches the target but oscillates. The allowable error should be reduced, as the drone switches targets once it is 0.5 meters within range. Secondly, the drone does not behave the same as in the simulation, as there are unexpected disturbances, causing unpredicted oscillations. In the lab, a 4-layer Cascade PID controller with manual combined tuning was implemented. However, after experimental testing, it was found that the Z-axis responded differently to the X and Y. Z was damped by the drone's weight and needed separate tuning. Following the lab, the code was updated to be user-friendly and allow for layer-by-layer, axis-by-axis tuning. The yaw in the lab behaved unexpectedly. This could be due to an incorrect sign on the coefficients or difference in tuning parameters required for the physical drone. Z was tuned using Ziegler-Nichols. Ku was found by setting Ki and Kd to 0 and then increasing Kp until oscillations occurred. Pu was found by calculating the period of oscillation. Using these values, Ziegler-Nichols formulas were applied to the data and the new Kp, Ki, and Kd replaced in the code. Each layer was tuned separately. Ziegler-Nichols didn't work well for X and Y due to their dead time dominant behavior, so manual tuning was implemented. High Kp can be used for a fast response, and increasing Kd helps damp oscillations, but also slows the system down. The drone's rectangular frame made X slightly more sensitive than Y, but joint tuning for X and Y still worked sufficiently well. Yaw was controlled by a simple PID controller with manual tuning. The drone turns in the shortest path. The drone successfully achieves target yaw. Even though the values look different, they are equivalent. Thank you so much for listening. References and links to the code can be found in the description.